Where? Okay. Anything else we need to talk about? Okay, let's get going. So today we're going to finish talking about linear transformations and then jump into 2.1 with linear algebra, matrix algebra. So that's our plan for today. So I thought we'd actually completed linear transformations, but when I was looking at my notes, there's still a handful of things that are happening down here. So here's the last bit of the linear transformations, and we'll try to dig up some examples to try to see what these actually mean. So the first thing we're going to talk about here is the standard basis vectors. And then from there, you guys probably know about the standard basis vectors, but we'll talk about that. And then from there, we'll talk about the matrix representation based on those standard basis vectors, because later on, we'll talk about changing the basis, and we'll have new matrix representations for a change of basis. So for now, let's talk about standard basis. In R2, standard bases are given by E1 and E2. In R3, it's given by E1, E2, E3. So E is our symbol for standard basis. You might know E1 and E2 in R2 better as the I and J vectors. That's probably what they use in physics or in Calc 3 because they're standard. They just call it I and J. And then in R3, they would say I, J, K. And of course, the I in R2 is slightly different from the I in R3 in that in R2 it's only two-dimensional, in R3 you have three components. And so I don't know if there's any good way to distinguish the I in R2 versus the I in R3, except to say that if you know in R2, then the I just means it's 1, 0, and if you're in R3, the I just means it's 1, 0, 0. So it's just a number of components. So in general, the ith basis vector will just be zeros everywhere except for the ith component. So for example, in R5, we can say E sub 2 is going to be the vector 0, 1, 0, 0, 0. Is that 5? 1, 2, 3, 4, 5. Yeah. So that's just notation, and that's how we'll define the standard basis vectors. Zeros everywhere, 1 in some slot. That would say, you know, second slot, second component is going to be 1, everything else with zeros. All right, now let's take a look at this theorem that says in R, if you have a transformation going from Rn to Rm, and it's a linear transformation, then there exists a unique matrix A such that T of x is equal to A times x. So this, you know, we've already made the relationship between the transformation and some matrix, if it's a linear transformation, and the matrix A. And so this just tells us that there's a unique matrix whose jth column is a vector T sub E, or T of E sub j, where E sub j is a standard basis vector. So what they're saying here is that we can construct, if we have a transformation, we can construct the matrix just by looking at what happens when we put a standard basis vector into the transformation. And we kind of saw that already when we were doing some examples, but let's take a look at how this theorem applies to some of the examples, or one of the examples that we've done already. So I'm going to take a look back in our notes and see if I can find an example from a linear transformation. Let's just select this linear transformation here. As our example. So let's backtrack and remind ourselves that this is a linear transformation, and this is well, transformation first of all. And can you tell me, just by looking at this, it goes from R what to R what? What are its domain and codomains? You understand the question? So what kind of vectors can I put in, and what kind of vectors are going to come out? So Harbad says it's R3 to R2. You guys agree? Why? Why not? Okay, let's take a look at the output first of all. If we take a look at the output, that might be easier. This T of X is equal to a vector. Now this is a vector, right? It's not a matrix right now, it's a vector. How many components do we have in this vector? 2. So that's going to be our output, right? So this has 2 components, 1, 2. So that's going to be our output. Now, what kind of vectors do we get to put in? Our R is some x1, x2, however far we need to go. How far the x subs get to go here? There's up to 3 subs for here, right? And that's the largest number that we have, so it's probably going to be from R3. And so we could probably get up to R3 in here, but not any more than that. So what kind of matrix should I come out with here? Remember how to read this? Our matrix A that we're trying to construct should be a what by what matrix? It should be a 3 by 2 or 2 by 3?
2 by 3.
Okay. So it should be a 2 by 3, right? All right. Now, what we want to do is we want to take a look at your inputs here, because those are the vectors that you get to put into the transformation. So this is coming from R3, so we want to be able to put in 3 matrices, all right, or 3 matrices, 3 vectors. The standard basis vectors for the domain, E1, E2, and E3. So again, it's 3-dimensional, so it's the IJK vectors. Oh, I don't have my, this is going to mess up my notes a little bit here. I thought I got this fixed. Excuse me while I change the size of my paper. So let's see what happens when we put E1, E2, and E3 in here. So let's put E1, E2, and E3. So T of E1 is equal to T, and then I'm going to put E1, which is what? So it should be 1, 0, 0 in R3, right? That's our domain. So let's put 1, 0, 0 in there. So x1 is equal to 1. What? Why is it 1? Well, no. This is just the E1 that I'm putting in, and then I'm going to get 5. Well, it'll come out to be 5, 0, 0 or 5, 0, right? So we're just putting it in, and then what we're getting out here is that x1 is equal to 1, and then x2 and x3 are all equal to 0. So that's just going to give me, for my first component, 5, and my second component is 0 plus 0, which is going to be 0. Okay. So what they're saying in the theorem is that I'm going to get to put this now into the first column of my matrix A that I'm coming up with. Okay. So that's the first one. The second one, T of E2 is going to be T of 0, 1, 0. And so this is going to give me 0 for x1, and x2 is going to be 1, and x3 is going to be 0. So this is going to give me -2, and this is going to give me 1 and 0, 1 plus 0. So it's going to give me -2, 1 as my vector, right? And then the last one, T of E3, is going to be T of 0, 0, 1. So x3 is going to be equal to 1, and x1 and x2 are going to be equal to 0. Okay? So basically our matrix A is equal to just these vector outputs that we got for putting in the standard basis vectors, and then we're going to make them into the columns of our new matrix. Yeah. We figure it out by looking at the dimensions of the domain and codomain, and then we just say it backwards. Yes? So this tells me that I'm going to put in 0 for x1, 1 for x2, and 0 for x3 into this output. And so when I do that, all I get is -2 and 1. Anything else? Any other questions? Because we already know how to do it. This just formalizes the way to find a matrix. So like I said, later we'll talk about changing basis. So this is the basis vector set that we have, the standard basis vector, right? If we change the basis vectors to not be 1, 0, 0, 0, 1, 0, and 0, 0, 1, if we change the basis vectors, then we're going to have a different matrix. Okay, so there's nothing that says that R3 can be represented by the E1, E2, and E3, the IJK vectors. That's what we always do because that's the easiest representation from R3. But if for some reason, whatever those reasons might be, we represent R3 with 3 new vectors, then I'm going to have a different matrix that would still be representing the same transformation. Okay? Yes? So now I can use this matrix instead of saying, if I want to figure out, that's the thing that we've done before. If we want to figure out what T of 1, 2, 3 is equal to, instead of going through this definition of the transformation, I'll just say, oh, that's the same thing as A. Well, I'll put A for now. A of 1, 2, 3. So now it becomes a matrix multiplication. 5, -2, 3, 0, 1, 4, 1, 2, 3. So now it's a matrix multiplication that I can just compute to give me the same result as if I was putting the 1, 2, 3 into the matrix, into the transformation. Yeah. I don't know if changing the colors would be a representation. It could be, yeah. So maybe your transformation changes one of the colors or takes out one of the colors or something like that, and then so you can just multiply by an appropriate vector. Maybe, could be. Anything else? Okay. All right, so I think that wraps up our quick overview of linear transformations, and we're going to keep going back to the idea of linear transformations as we study all the different aspects of matrix algebra and linear algebra in general. So later on, when we change basis in, I don't know what chapter that is, but when we start doing change of basis stuff, we'll see if we can pull it back to this idea of a linear transformation and see what it means. All right. So now let's move on to chapter 2. No, I think it's already done. All right. So chapter 2 just gets us acquainted with matrices in general, although we've already been talking about matrices. Kind of lays the groundwork for working with matrices. So it talks about components of a matrix, talks about a couple of special matrix or one special matrix, the identity matrix, and then we'll do things like add, subtract, multiply. Scalar multiply and multiply. So matrix operation. In this section, we're going to talk about matrices as a mathematical model or object. Just like it's like you know, when you learn about numbers back in kindergarten, I guess, and then you learn how to add and subtract and multiply numbers. Same thing here. We're going to talk about matrices, and we're going to do things like add, subtract matrices. So they are two-dimensional array elements. We have identifying matrices as a collection of column vectors. So this is the way we're going to kind of look at matrices a lot. Instead of looking at matrices as an array of numbers with different numbers in different rows and different columns, one really common way we're going to look at matrices would be a collection of column vectors. So the column vectors are going to be represented by, well, in this particular example, A1 through AN, where each A1 has, like, A1 has M elements, and A2 has M elements, A3 has M elements, etc. So let's take a look at our example matrix. We had an example matrix where we had what was the matrix that we came up with? It's fairly simple, right? It's a 3 by 2 matrix, wasn't it? 2 by 3. What was it? 5. So let's use this as our example, and let's see if we can identify the different ideas that they're bringing up here. Let's call this matrix A. So we can call A, or we can represent A as a collection of column vectors, right? Maybe I should just type. So the column vectors can be, if we call A a set of column vectors that look like this, it would be A1, A2, and A3, right? Since there's 3 columns. And then so we can find values for A1, A2, and A3. So what's A1? Right? And A2 would be -2, 1, and A3 would be 3, 4. Okay. Sometimes we might be interested in pulling out some entries, like the ijth entry. So we can say the 1, 3 entry is equal to what in this case? We would probably call it A sub 1, 3. Sometimes they put commas in between here, so it doesn't look like it's 13. So sometimes they put A sub 1, 3. But if they don't put a comma and you don't have 13 columns or anything like that, then you know it's the first row and the third column. So in our example, what's A1, 3? 3 in the first row and first column, right? So we can have a collection of these things, and we can pull out an entry from a matrix by calling it A sub whatever the row is and whatever the column is. So that's another example. In our third example, well, it's not a third example, but looking at the diagonal entries, for looking at the diagonal entries, we're looking at the 1, 1 position. What's in the 1, 1 position? 5. And then we're also going to be looking at the 2, 2 position. 1. And I think that's all we have. We have more columns than we have rows. And so when we're looking at the diagonal entries, though, we're just looking at the main diagonal. So the main diagonal runs down here in the main diagonal. So visually, you can just see it's the diagonal of a matrix starting from the upper left-hand corner and going downwards in the diagonal. Okay, so those ideas make sense? So that's how we'll identify matrix. We'll be able to look at the entries. We will be able to look at a matrix as a collection of column vectors, and we will be able to identify diagonals of matrices just by going down the diagonal from the upper left. All right, the next idea here is the identity matrix. The identity matrix will be denoted by capital I. And if we need to make sense out of this, we'll put a subscript to say the dimension of the identity matrix. But if it's clear what we're talking about, then we don't usually put the subscript. So if we're talking about being in R2, we know that the identity matrix is going to be a 2 by 2 matrix. But in case it's not clear, we'll specifically put a subscript to say what the dimension is for the identity matrix. So the identity matrix is going to be a matrix with 1 in the main diagonal. Oh, first of all, identity matrix has to be a square matrix. Same number of rows, same number of columns, and it'll have 1 in the diagonals, it'll have 0 everywhere else. I don't know why I need to put this here, but just for an example, I sub 2 is going to be 1, 0, 0, 1. I sub 3 will be 1, 0, 0, 0, 1, 0, 0, 0, 1, etc. Okay. So we'll see identity matrices are actually matrices that are like, well, it's called identity because like the multiplicative identity, whenever you multiply something by 1, you're going to get the original number back, right? 5 times 1 is 5. So the same thing when we do matrix multiplication, we multiply this by, we multiply something by the identity matrix, you're going to get back the original matrix. All right. Let's take a look at some properties for addition and subtraction, and maybe we'll take a look at adding and subtracting matrices, and then we'll take a look at some, should be on the next page. So when you're going to add 2 matrices, the 2 matrices have to have the same size. Otherwise, you're not going to be able to add them. So it doesn't matter what the size of the matrix is, as long as it's the same size, then you should be able to add matrices. And then so there's a couple more formulas here, a couple more properties that talk about multiplying matrices. So let's talk about addition and subtraction and scalar multiplication. Subtraction can be like a scalar multiplication with an addition happening. So let's do some examples. I think I have some examples here. But what's that? Let's I'm stuck. Let's do some examples that involve scalar multiplying and adding and subtracting, or adding, and then let's put off the multiplication until the next page after we take a look at a couple of other properties. So this is not really, maybe not related to properties, but let's take a look at what -2 times a would look like. So -2 times a takes a look at the A matrix and multiplies every single entry by 2. So this is -2 times 2, 0, minus 1, 4, minus 5, 2. And then, so everything in there gets multiplied by -2. So -4, 0, positive 2, -8, positive 10, -4. Okay. Nothing to it. All right, let's take a look at what b minus 2a might look like. This says that we have b 7 minus 5, 1, 1 minus 4 minus 3. So minus 2, it's like saying plus -2 times whatever. So let's put that -2 times 2, 0, 1, 4 minus 5, 2, -1. So this is going to be 7 minus 5, 1, 1 minus 4, -3. And then we can think about adding this after we distribute the -2. I think that's the same matrix as this. So when we add matrices, just like when we add vectors, it's component by component. So we will have the same size, 4 or 7 minus 4, and -5, 1 plus 2. We have -7, 6, and -7. Okay. So those are some of the basics. Let's take a look at some of these other things that we cannot do. A plus C, 2, 0, minus 1, 4, minus 5, 2, plus C is 1, 2, minus 2, 1. So this will not work because one matrix is a 2 by 3, the other matrix is 2 by 2. So cannot add. How should we say this? Undefined, not defined, cannot do. What? Yeah. So cannot add, not the same mention. So you have to have the same size matrix to be able to add, subtract. Okay. So let's go back to the properties here. We can give these properties names. So when you're able to switch the order of addition, what's that called? What? Commutative. So commutative addition, additive, commutative. And then when you reorder, regroup 3 or more, what's that called? Associative. When you add 0, do you guys know what that's called? No? So the identity matrix is dealing or referring to multiplicative identity. When you're adding a matrix like 0, this 0, by the way, is a 0 matrix. It's not a number. It's an actual matrix of the same size as A. And so when you add 0 to something, you're going to get the original thing. It's called additive identity. Here are a couple of distributive properties. Distributive properties. And then this one is another associative property, but with scalars. Okay. So it means if you have a scalar times a matrix, you can take the scalar out and multiply the scalars together first, and then multiply it times the matrix. There's similar vector properties that deal with these things that we didn't really talk much about, but they're here. We'll take a look at some vector properties, and we'll take a look at vector spaces in chapter 4. All right, any questions for now? What? Associative with scalar. Okay. All right, now let's take a look at some multiplicative properties. Let's do some examples first of multiplication. Do we have room on this page? So we've started to talk about multiplication already, kind of. Let's do multiply C times D first. Where C is equal to 1, 2 minus 2, 1, and D is equal to 3, 5 minus 1, 4. So let's talk about matrix multiplication and how it works. You've already started to multiply a matrix times a vector with the A times X expression, but now let's take a look at how matrix multiplication works. So the matrix multiplication, the general idea here, and they talk about it a little bit differently. They talk about it with respect to coming up with multiplying by vectors or something like that, scalar multiplying by vectors. But let's talk about it in terms of how we're going to try to do this quickly. So what you do is you take a row of the first matrix, and then you're going to, I'll say this in quotes, multiply it with a vector, with a column from the second matrix. And by multiply that, it's kind of like a dot product kind of thing. And so in this particular scenario here, the 1, 2 gets multiplied by 3 times negative 1. You actually multiply 1 times 3 plus 2 times negative 1. And then you're going to get the value for that, whatever value you get when you do that multiplication. And that's going to be in that 1, 1 slot. Okay, and then you take the row and then a different column, and then you're going to do that multiplication. So in that row and column combo, you're going to get 1 times 5 plus 2 times 4. So that's going to be that second row. So look at what's happening here before we go on. You're multiplying the first row with the first column, and then you're at the 1, 1 spot. You're multiplying the first row times the second column, and you're at the 1, 2 spot. Okay, so whichever row you're dealing with and whichever column you're dealing with in that multiplication, that's going to be the ijth entry. If you're in the ith row and the ith row in the first matrix and jth column in the second matrix, then your result is going to be in the ij position in your product matrix. All right, so we keep going and multiply the second row with the first column. So we got negative 2 times 3 plus 1 times negative 1. again, you're matching the rows, so it's a second row from the first matrix times the first column from the second matrix. You're looking at the 2, 1 spot. And then finally, it's a second row. Ooh, now you can't see. And the second column, second row, second column, so that's the 2, 2 spot. The 2, 2 spot, I would have minus 2 times 5 plus 1 times 4. Okay, so let's just go ahead and simplify all this. Uh, 3 minus 2 is 1. 5 plus 8 is 13. Negative 3 minus 1 is negative 7. And negative 10 plus 4 is negative 6. Okay. And I think we talked about this already when we're doing matrix multiplication. Certain matrices that we can multiply, some certain combinations of matrices that we can multiply. Here we have a 2 by 2 matrix. We're multiplying it with a 2 by 2 matrix. And remember that we have to get the number of columns from the first matrix to match up with the number of rows in the second matrix. And then your result here is a 2 by 2 matrix. And so that works out okay. All right. Any questions? Now let's take a look at one that we can't do. I think we can't do this. So AC, A is the matrix 2, 0, negative 1, 4, negative 5, 2. 2, 0, negative 1, 4, what is it? Negative 5, 2. Multiply that with 1, 2, negative 2, 1. That's C. So if you try doing this, attempt doing this matrix multiplication, we'll see that when we try to multiply the first row with the first column, first row and the first one, the first column, here we have 3 components. We have we have 3 columns and only 2 rows. And so when we do this multiplication, it doesn't match up. So in fact, this is a 2 by 3 matrix, and you're trying to multiply by a 2 by 2 matrix, and then these two don't match. So this is not defined, cannot multiply. Okay, so we can't multiply this, so it's just going to be undefined. So for you to be able to multiply matrices, you need to have the number of columns in the first matrix match up with the number of rows in the second matrix. All right. Okay, let's try one more matrix multiplication. Is this okay? Is this this is really boring. There's nothing deep that's happening here. It's just algebra. All right, let's get through it. All right, you guys are all falling asleep, man. At least half of you. I mean, I could see your eyes are glazed over. All right, let's take a look at doing, I wanted this in a different color. So, can we do this in your head already? You got 3 minus 10, negative 7. We got 6 plus 5, 11, minus 1, minus 8, and minus 1, minus 2, plus 4. Okay? It's good. You guys can do it in your heads already. So we could just do that when we're doing matrix multiplication. All right. Oh, this is CD, sorry. No, this is DC. Anyways, I wanted to do this example and compare it with the first example that we did. And what do you notice? What is C times D? The other one we just did is D times C. Not equal to each other, right? So keep that in mind. And we'll list down some properties for multiplication. So we're going to assume that B and C, A, B, and C are appropriate sizes, whatever they might be. And the first one is what's this property called? What? What? No, the first property, property A. So this is associative property, this time for multiplication. So associative property for multiplication. So we had an associative property for addition, right? And this is now the associative property. The next one is what? Distributive property. And then this one is also distributive. Now, remember that when we did our example of CD and DC, they didn't equal each other. So multiplying something from the left and multiplying something from the right is different. And so we just say this is distributive from the left and distributive from the right, but let's just call it distributive. And then here's another associative property, but this time you're rearranging matrices. So and then the last one is our identity property. And so we had an identity property for addition. This is an identity property for multiplication. Oh, because it depends on where you multiply this by, right? So let's take a look at our example. What was our A equal to in the last part? And 0? 2. So imagine multiplying this by an identity on the left side. Wait, this is a what by what? There's a 2 by 3 matrix, right? 2 rows and 3 columns. So let's imagine multiplying this matrix by an identity on the left side. So if I need to multiply this by an identity on the left side, and identity matrices are always square matrices. What's the size of this matrix? If this is a 2 by 3, this is a what by what, it has to match with this, right? So this should be a 2 by 2. So 1, 0, 0, 1. And if you do this multiplication, I encourage you to just work it out. This should be equal to 2, 0, minus 1, 4, minus 5, 2. Now, if we take the same matrix, 2, 0, minus 1, 4, minus 5, 2, and then multiply it by another square matrix on the right side that's an identity, this is a 2 by 3, and then this is a what by what. It has to be the same, right? And so it has to match with the number of columns this time. So it has to be a 3 by 3 matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. And so you do that multiplication, you'll see you're going to get the same matrix because it is the identity. Again, I encourage you to actually go through the motions of doing the multiplication to see that it actually will come out to be that. You can't just believe what I say up here. Might not be true. Okay. So, any questions? We're associative. We can distribute from the left, distribute from the right. We can multiply by identity on the left, on the right, whatever that appropriate size might be. And so a couple of warnings and cautions. When we are used to solving for equations in algebra, we used to just, we say we divide by something or multiply by something and then we can get rid of something. There's all that talk about doing that, but when we're dealing with real numbers, we know that they're commutative. When we're dealing with matrices, it's not commutative anymore, so we have to be careful about how we approach things when we're solving for things. So first of all, in general, AB is not equal to BA. In general, it might happen that it's equal if you switch the order, but that would be, I wouldn't say rare, but that wouldn't happen in general. So in general, you can say it's not commutative. And that's the biggest thing that we need to get out from today is that matrix multiplication is not commutative. Cancellation laws do not hold in matrix multiplication. We can't say that if AB equals AC, then you can, quote, cancel the A's out, right? So we're used to doing that when we're solving for things in algebra, but in algebra, things can switch orders, and we have a nice definition for the inverse, like the reciprocal of a number. So dealing with numbers is different, slightly different from dealing with matrices, and you can't just, quote, cancel out the A. And then the product, the zero product that we learned in algebra also doesn't necessarily hold. So if a product AB is equal to 0, then you can't just conclude that A is equal to 0 or B is equal to 0. Maybe they are, but it's not a safe conclusion because you could have two non-zero matrices and you multiply them together, they're going to get 0. So we have to be careful with that as well. Any questions about some of these warnings? So the warning number 2 and 3 kind of depend on the idea of inverses, which we'll talk about next time. But the way the inverses work is different for matrix multiplication. And that's one of the things that we have to be careful about. I did see some interesting problems to do here. Let's take a look at problems that I kind of just stole from the book. Let's try to look through these problems. Number 8, how many rows does B have if B times C is a 3 by 4 matrix? This is a good clicker question, huh? So, how many rows do you think it should have? Should have 3? Should have 4? Should have 3? Okay, let's check. So B times C is equal to whatever the result is. The result is supposed to be a 3 by 4 matrix. So it looks like this should have 4 columns for sure, and these two numbers should match up, and this should have 3 rows. And what number does this have to be? Does it have to be 4? Does it have to be 3? Does it have to be anything? It could be anything. So if you have a 3 by 5, multiply that by 5 by 4, your result is still going to be a 3 by 4 matrix, right? If you have a 3 by 10, multiply that by a 10 by 4 matrix, you're still going to have a 3 by 4 matrix. So it doesn't matter what the number of columns is for the first one and the number of rows is for the second one, as long as they match. They just have to match, right? All right, let's try to do next one, number 9. For what values is this going to be equal to each other? How would we do that? It looks like we need to multiply it out, right? So 2, 5, minus 3, 1, 4, minus 5, 3, and k. So let's multiply AB first. So this is a 2 by 2, a 2 by 2. Your result should be a 2 by 2. I have 8 plus 15, 23. Negative 10 plus 5k. Negative 12 plus 3. And 15 plus k. So that's what AB is equal to. Let's take a look at what BA is equal to. So this is 8 plus 15, 23 again. That's a good sign. What is it? 15. And then we have 6 minus 3k. 15 plus k. This is BC or BA. Now, if we want them to equal each other, all the values should be equal to each other. The 23, good thing that they're equal. The last one over here is equal to itself, but if we try to solve for it, we're going to get 0 is equal to 0 or a true statement or whatever. So it looks like the only other things that we can work with would be these two equal each other. 5k minus 10 is equal to 15. And also these two equal to each other. 6 minus 3k equals negative 9. And since we're only solving for one variable, we hope that we'd actually get the same values here. Otherwise, it'll not work. So what is it? K is equal to 5. And if we do that over here, it's 5. Okay, so if K is equal to 5, then this becomes commutative. Now remember, they're not saying that AB is never going to equal to BA, right? They say it's not necessarily going to equal to that. So if you look at the warning, in general, this is not true. In some cases, you can make it true by just changing one or two of your numbers. Okay? All right, so number 10, you can work that out. So just do a couple of matrix multiplications and show that they're, you know, that last warning doesn't, or the second warning doesn't necessarily hold. A couple more ideas. And these ideas aren't really based on matrix algebra. Why is this so big? Why is this so small? All right. Should be an m by n. So powers of a matrix. A matrix to a power is the same thing as you would know it to be in regular algebra. It's multiplying the matrix k times. Now they have to have the same size, you know, it has to fit the size, so you can only do this for square matrices. Now the other aspect is that we're going to be having these matrices being multiplied with a vector, or, you know, a column vector, a column matrix that represents a vector. So if A is a non-zero matrix and X is some vector in Rn, then AK is a result of left multiplying X by A times. So what that says is that you have A times X, and then you get whatever result you get here, you're multiplying by A again, and then you're multiplying by A again, and you're multiplying by A on the left side. So for example, this is equivalent to A cubed times X. No, A squared, 1, 2, 3. Yeah. So 1, 2, 3, 4 squared is not equal to 1 squared, 2 squared, 3 squared, 4 squared. So it's not equal to that. So a squared instead is actually 1, 2, 3, 4 times 1, 2, 3, 4. And whatever that is. It just means it's a square matrix. So 2 by 2, 3 by 3, 4 by 4. And you can't square a rectangular matrix because a 2 by 3 times a 2 by 3 wouldn't work. It must be a square matrix. Otherwise, the general rules won't hold. So one more, the transpose of a matrix. Oh, and some properties. You can write fast. Actually, maybe I'll challenge you one of these days to not take notes at all in class one day. See how it is, right? Because all the notes are online, videos online. Let's see. We'll have that as an activity, and we'll see how it works out. All right. So the last thing is the transpose. Transpose of a matrix is switching the rows and columns. So 1, 2, 3, 4, 5, 6. Transpose is 1, 2, 3, 4, 5, 6. Okay. So with this idea of a transpose, there's some properties. A transpose is the original matrix. The other properties are kind of weird. Not weird, but might not be so expected. But the transpose of a sum is a sum of a transpose. And if you're taking the transpose of R times a matrix, it's like taking the transpose of the matrix first and then scalar multiplying by R. And you can see that when you distribute the R to everything, you just take it all out. And so it doesn't matter what the shape of A is anyways. And now this is really the most interesting one. The transpose of the product is equal to the product of the transpose, but in reverse order. Now that's a little trickier to imagine, but I'll let you imagine that between now and Wednesday. Okay. So next time we'll talk about inverse of a matrix, and we'll have a bunch of ideas put together as a result of what it means for a matrix to have an inverse. All right, see you guys next time.